All right. Hi, everyone. We're back and we're talking about equilibrium. So we're going to jump right in and start talking about equilibrium constants and how we can use them, how we can apply them, how we can use them to tell us things about the equilibrium state. So let's just jump right in and should be good here. All right. So really what we're talking about today is what is the meaning of K, this equilibrium constant expression. So just a quick refresher, when we write our equilibrium constants, we remember that it is the product of the concentration of the products raised to their coefficients divided by the product of the concentrations of the reactants raised to their coefficients. So in this particular equilibrium expression where we have two molecules of nitrogen dioxide dissociating to give us, or decomposing to give us, two molecules of nitrogen monoxide and one molecule of oxygen. In our numerator, we're going to have the nitrogen monoxide squared times the concentration of oxygen squared. And in the denominator, we're going to have the concentration of nitrogen dioxide squared. So our K expression is going to look like this. And again, that reminder that we're going to use square brackets to represent concentration. If we were writing a Kp, a K pressure, then we would want to make sure that we are using parentheses and we are using the convention of P subscript the species. So we've written our K expression. Next thing is just another quick reminder that if we have a heterogeneous equilibrium, it's not affected by the concentration of a pure liquid or a pure solid. And so when we write that equilibrium expression, that constant expression, we're going to leave out any pure solids or pure liquids. And so our phosphorus pentachloride being a pure solid and our phosphorus trichloride being pure liquids are not going to be in the equilibrium expression for this decomposition reaction. And so our K is simply going to be equal to the concentration of chlorine. We could also write, because this is a gas, we could write a Kp expression for this one. So Kp would be equal to the pressure of the chlorine. Pretty simple and straightforward. If it's a pure solid or a pure liquid, leave it out. K expression is products raised to their coefficients over reactants raised to their coefficients. So what can this tell us, or what information can we learn from it? So if we know K, we know the value of K, and we know the concentrations of some of the species at equilibrium, then that's going to allow us to calculate the concentrations of any other species at equilibrium. As an example, in the dissociation reaction of acetic acid, so acetic acid dissociating in the presence of water to give us hydronium ions and acetate ions, we know the KEQ of this dissociation reaction, it's 1.8 times 10 to the negative fifth. We also know that at equilibrium, the concentration of both the hydronium ion and the acetate ion are 5.2 times 10 to the negative third molar. And it asks us to find the concentration of the acetic acid. So our first step is always going to be to write the dissociation reaction, or write whatever the equilibrium equation is. So in this case, acetic acid plus water yields hydronium ion and acetate ion. And we know which direction to write it because it says it is a dissociation reaction. So we know that the acetic acid and water are reactants and the hydronium ion and acetate ion are products. Now we can write our K expression. Again, because water is a pure liquid, we're going to leave it out of this K expression. So we have K is equal to the concentration of the hydronium ion times the concentration of the acetate ion divided by the concentration of acetic acid. And now it's just a matter of plugging in and solving algebraically. So we plug in the value of K, 1.5 times 10 to the negative eighth. We plug in the two values for the concentrations, 5.2 times 10 to the negative third. And then we solve for the acetic acid concentration. And that gives us an acetic acid concentration of 1.5 molar. So once we've written the expression, we've written the K expression, then we're just solving algebraically. Turning this around, if we know the concentration of all the species at equilibrium, then that's going to allow us to calculate the value of K at a given temperature. So if we have the synthesis reaction between hydrogen gas and sulfur to form hydrogen sulfide gas, and we're given the concentration at equilibrium of hydrogen sulfide and hydrogen, and then we're asked to find the KEQ for the reaction. So first we need to write our synthesis reaction. So our hydrogen gas plus solid sulfur yields hydrogen sulfide gas. Now we're going to write the K expression. Because sulfur is a solid, we're going to leave it out of the K expression. So we just have the K is equal to the concentration of hydrogen sulfide divided by the concentration of hydrogen. Again, because this is a gaseous reaction, we could write this as a Kp, but the information that we were given is concentration, so that's why I wrote a Kc or a Keq. Now, again, we're just plugging in values and solving. So we have 0.0135 divided by 0.198, and that gives us a K value of 0.0681. Okay, one last practice. We have a diagram here that represents the equilibrium between two isomers of dimethyl chloride, and the table provides the data that was collected in an experiment to determine its equilibrium constant at 490 Kelvin. So we ran this simulation or this reaction at 490 Kelvin, and now we run a second experiment at the same temperature, which is important because otherwise the K would change. And we find that at equilibrium, the concentration of Z is now 1 instead of 0.8. So it asks us to find the approximate equilibrium concentration of Y in the second experiment. So I'm going to pause our sharing here for just a second and we'll switch to the board. So we know that the concentration, we're going to first have to find the K value, and then we're going to find the new concentration at the new equilibrium. So let's take a look. So we're going to find K first. We know that K is equal to the concentration of Z over the concentration of Y. We're just using these because they're isomers, so they have the same expression. So we know that at equilibrium, the concentration of Z is 0.80, and the concentration of Y is 1.2. And so that's going to allow us to find the K value of 0.67. And once we've found that K value, we can now use that K value, since we're still at the same temperature, to find the new concentration of Y. And so we can use K equals the concentration of Z over the concentration of Y equals concentration of Z. Oops, we know our concentration of Z, 1.0 over the concentration of Y. And we know that still equals 0.67. And so we have the concentration of Y equals 1.5. So just by using the initial equilibrium to find the value of K, and then using K to find the concentration of Y, we're just turning this all around and using algebraic manipulation. So let's jump back in. Because we've now solved that one. Okay, so let's talk about just looking at values of K and using them to tell us about a reaction. So when we look at a value of K, if it's a large value of K, and generally speaking, when we're talking about large, we're talking about anything in the value. Well, large means anything over 1, okay? If it's over 1, that means we're going to have more product than reactant. If it's a really large number, like in the range of 10 to the third, that means it's going to nearly go to completion. So large values mean that it's product favored. We will have more products than we have reactants. Really large values mean it effectively goes to completion. Small values, that means anything less than 1, signifies that the reaction is reactant favored. So that means that when we reach equilibrium, there's going to be more reactants than products. So very little reactant has been converted to product. So you should be able to use the value of K, whether it's large or small, to determine the relative concentration of products and reactants at equilibrium. So let's look at a quick practice problem. So we have this table. It gives us the K values for 2 different equilibrium reactions at the same temperature. In each container, we add a half mole. Okay, let's see if we can finish this up quickly. Okay, so we have our data carried out for these 2 reactions. In each of our 1 liter rigid containers, we add a half a mole of each of the appropriate reactants, and the reaction is allowed to reach equilibrium. So it says, based on this information, which of the following correctly compares the relative concentrations of the bromine monochloride and the nitrogen monoxide present inside their respective containers. So when we look at these, we can see that the KEQ for the bromine monochloride is 10. That's much larger than 1. That's a pretty large KEQ. And when we look at the KEQ for the nitrogen monoxide, it has a very, very tiny value, 4.2 times 10 to the negative 31st. So that means that when this equation reaches equilibrium, there's a tiny, tiny, tiny fraction of a mole of nitrogen monoxide that's been produced. But this reaction, we've produced lots of bromine monochloride. So even before we start to look at our choices, we know that bromine monochloride is present in much larger quantities than nitrogen monoxide. So we can immediately rule out A and D. But let's take a look at B and C, because now we have 2 correct initial parts of the answer. Now we need to look at what the justification is. So B says because bromine and chlorine are larger molecules that can collide more frequently to form products. And C says because the much larger KEQ for reaction 1 means that a much higher concentration of products will be present at equilibrium for reaction 1 compared with reaction 2. And that's the reason that we know that the bromine monochloride concentration is much higher. So we're going to choose C. And we'll stop there for today. If you guys have questions, let me know, and we'll do more practice problems tomorrow.